Hello and welcome to the continuation of lecture 2 of module 12, which is on the linearization of state space dynamics. So, if you remember what we have done in the previous lecture, it was part 1 of lecture 2. So, basically what we did was to consider a nonlinear system. So we modeled the nonlinear system, right. Then we computed the equilibrium points, okay, and we computed the Jacobian, which is you consider all the first derivatives of the Taylor series, and in general it is a n cross n matrix depending on the number of states that you have. So, you compute the Jacobian matrix, and then in order to compute the A matrix, you basically evaluate the Jacobian, all right, at an equilibrium point, right. So, this is the basic theory which we saw in the previous class. Now, before I go ahead with two very interesting examples for today, I just want to make a small note about the equilibrium points itself. Now, in the nonlinear case, which is what we are dealing with, in general you do not have a single equilibrium point, you can have multiple equilibria. So, if you consider a nonlinear dynamical system, it can have multiple equilibrium points. I will give a small example to illustrate that. Let us say I have got a nonlinear system of the following type. All right. Now, if you actually graph this, so you have x axis and you have the cos of x on the y axis. X of course will be in degrees or radians, however you like, and so cos 0 is 1. So, you will actually get a graph like this, right, and so on. Now, if you recall the definition of an equilibrium point, it is basically where the derivative goes to 0. An equilibrium point is a point on your in the space of the independent variable. So, it could be any one of these points where the derivative goes to 0. Now, you see that for this simple example of the cosine of x. So, if you look at the cosine of x and you try to compute the equilibria, you see that you have multiple locations, the angles that is, where the derivative of the dynamics actually goes to 0. So, this would be one place, you have this, so on and so forth. So, for this you actually have an infinite number of equilibria depending on, as long as x keeps on repeating. Okay. So, for a nonlinear system, it is not necessary that you have a single equilibrium point, you can have multiple equilibria. All right. So, with that in mind, let us actually go to two interesting examples for today. The first example is the predator prey model. And before going ahead with the mathematics of this, the reason why we introduce tigers, deers and other kind of things in a lecture in control systems or in control engineering is actually twofold. One is that the beauty of control systems is that it allows us to model in principle any physical system, and the physical system need not be a chemical process, it need not be just a electrical system, it can even be an ecological problem as what I am going to present today. It can even be a problem in economics, right, and so on. That is one thing. The second is that when we look at the predator prey model today, it is important to remember that the kind of dynamics which I will be talking about are also applicable when we model certain behavior in economics, in social behavior and so on. Okay. So, with that in mind, so let us go ahead with the predator prey model, and let us take the specific case of tigers and deers. Okay. So, these are two pictures which I have taken of the net, and they show a tiger and the deer in the Bandipur forest, and the male samba deer is native to the Bandipur forest. Okay. And one of the reasons why people do a lot of modeling for these tigers or predators in forest is because the tiger is basically a symbol of the well-being of the ecosystem. The tiger depends on the prey, the prey depends on say trees and grass and other kind of things. They depend on other subspecies. So, if the tiger is actually conserved, you are essentially conserving the entire ecosystem. Okay. So, that is why the predator prey models were historically developed. So, what is a predator prey model? First, let us look at the prey. Okay. So, let h of t represent the number of deers, and it is a function of time. Now, in this particular context of the predator prey model, t is not in seconds, it is typically in months or in years. Okay. So, that we need to keep that in mind. So, if h of t is the number of deers, in the absence of predators, we are going to make an assumption that the deer population keeps on increasing, which is an assumption I am making in my modeling, and that essentially follows this particular equation, which basically says that the rate of change of the population of the deers as a function of time, and time being in months or years, is a positive rate of change where RH is greater than 0 and H is basically the population of the deers. RH is actually greater than 1 to be more specific, right. And this particular parameter RH times H, RH essentially is the reproduction rate of the deers or the growth rate of that population, all right. So, as long as RH is greater than 1, we have the population of deers going on increasing, which is basically this what this equation talks about over here. So, we know that this cannot be really true in general, that the population of the prey keeps on increasing, because what this particular equation seems to be telling us is that as time goes to infinity or a very large time like maybe 5 years, 10 years and so on, the population of the deers, which was say for example 50 in the Bandipur forest, according to this equation would keep on increasing, right, which is not true, because your forest ecosystem cannot support such a large population of deers, right. And the way that we would model this constraint is to say that let k be the maximum population of deers which this particular jungle or the ecosystem can actually support, okay. And the number of deers cannot go more than k, and the way you would model that is by this expression over here, okay. And what this expression basically tells us, so this part is the same as what we have seen before, the growth rate or the reproduction rate of the deers. Then you have a 1 minus hk, okay. H is generally less than k in the case where k is very large. In the example where k is very large, let us say even approaching infinity, this term goes to 0. So, 1 minus h by k becomes 1 minus 0, which is 1, okay, and basically says exactly what we talked about before, that the growth rate of the deers is constant and it keeps on increasing and it can reach a very large number, possibly infinite. In general, h will be much less than k, okay, because the forest cannot really support such large population of deers, there is not enough food basically. And as long as h is less than k, this expression over here is less than 1, all right. And so that basically means that I do have a constraint on the total number of population of deers which my jungle can support. However, for the remainder of this talk, without any loss in generality, for the remainder of this talk, I will assume that k is very large, meaning I have this hypothetical jungle which can support as many deers as possible. It is not a correct assumption in reality, but we will go with that for now to just show the modeling capability of state space systems, okay. So, this slide basically concludes with the equation which we are going to consider as dH by dt equal to RH times H, okay. So, this is the dynamics of the prey in the absence of the predators, okay. Now, in the presence of predators, you see that this growth rate of the deers is now compensated by an interaction say parameter between the deers and the tigers, where L of t is the number of tigers in the jungle, okay. h of t of course as we saw before was the number of deers, and the parameter A is the interaction parameter between the tigers and the deers. Okay. So, we can see that now this equation basically says yes, I do have a growth rate in the deers because of reproduction and there is plenty of available food for them, but then I have a decay rate over here, okay, this negative term. This is the interaction when the tiger basically hunts the deer and the population of the deers go down, all right. So, this is our prey model. So, dH by dt equal to RH times H minus ALH, and it is actually an interesting exercise. I would like you to try this. This parameter over here, the product of the number of tigers and the number of deers, is your nonlinear term. Okay. This is a perfectly linear term. RH is a positive constant, H of course is the population of deers. This is the nonlinear term over here. I would like you to prove this on your own. Okay. So, that is the prey model. Now, what about the predator? Now, the assumption that we make for the prey model is that there is always plenty of food available, which is basically grass and other leaves which the deers eat, but for the predator it needs the prey, right. Now, let us say that the predator is, for whatever reason, it is unable to actually kill the prey and then have food, in which case you are actually going to see that the predators are going to starve to death. And let us assume, this may not be always true, let us assume that the rate at which they starve to death is an exponential factor, okay, an exponential decay, in which case we get this expression. So, when L of t is a number of tigers in the jungle, so the rate of change of the population of the tigers is this negative growth rate over here. Okay. So, this is in the absence of prey. In the presence of prey, the population of the tigers will obviously recover. Right now, they get food and they can they are healthy, they can reproduce and so on. So, every time I have an interaction between the tigers and the deers, the population of the tigers over a period of time, months, years, will be a positive growth rate. Okay. This is good for the tigers, not so good for the deers, but it is very good for the tigers. So, now this is the equation, the dynamics for the population of the predator, and again as in the previous case, I would like you to see and try to prove on your own that this product term between two variables, which are actually the states, between two variables L of t and H of t is actually a nonlinear term. Okay. This is actually what makes the dynamics nonlinear. Okay, very good. So, now we have two equations and it turns out these equations are coupled, right. So, you have H, which is a function of both H and L, and then dL by dt, which is a function of both H and L. So, if we just rewrite this in a matrix form, we essentially have this expression over here. Okay. This is again your classic state space thing, and this is not the A matrix as we call it in the linear case. So, this is basically x dot equal to f of x, where my state vector x is basically h of t and L of t, all right, and this is the f of x bar over here. Okay, very good. So, what we have done so far now is to basically capture and to actually write down the nonlinear dynamics of the predator prey problem, right. That is the first step. Now, the second step would be to compute the equilibrium points and we go to the Jacobian and so on. So, let us see how we do that. Okay, before we do that, there is an important modeling assumption which we should make. So, if you see in this slide, we have assumed that the interaction parameter between the tigers and deers is the same. Now, this is not true in general and it is not true for an interesting reason, because every time an interaction takes place between the tiger and deer, okay, typically the deers usually escape. Most hunts are not successful. Okay. However, when an interaction actually does take place, meaning the tiger manages to make a kill, the deer population will definitely reduce immediately by at least one, depending on how many the tigers kill. But this does not mean the tiger population is going to increase immediately. right. So, the population of deers decreases because one of them was killed, but the population of tigers will not increase immediately, it takes a much longer time. So, this interaction parameter A, it cannot be the same for both, and more specifically in our case the interaction parameter for the deers will always be greater than the interaction parameter for the tigers. Okay. Furthermore, the growth rate of the deers is much larger than the death rate of the tigers. Again, it is an assumption, and these assumptions are usually proven to be valid in actual field studies. So, we take this basic model, and with the assumptions which we have placed over here, we get a new model which is exactly, it looks the same. We made certain assumptions on the parameters, right. So, we basically assume that A1 is larger than A2, where A1 is the decay rate for the deers when the interaction happens, and RH and RL are the respective parameters for each of them. Okay. So, now we take this set of coupled differential equation, and we will compute the equilibrium points. Now, and then of course linearize it, and we will go ahead with that. So, the way you couple, the way you compute the equilibrium points, we have seen before for a system of the type f x dot equal to f of x, and equilibrium point x naught is such that when you evaluate the function f at x naught, it is equal to 0, which is basically saying that x dot equal to 0 when evaluated at x naught, all right. So, we are going to do the same here, we are going to set each of these parameters to be equal to 0, and we will see what is the solution of these two equations. And that is of course fairly simple, because in this case it is just algebraic expressions over here. So, we set dH by dt equal to 0, we will see that this basically means RHH minus A1 LH is equal to 0. Okay. So, this basically gives you, let us just call it equation number 1, we will come to the other one later. And we do the same thing with dL by dt, we set this equal to 0, and this basically would mean that RL times L plus A2 LH equal to 0. We have two equations and two unknowns, the unknowns are L and H, and remember these are functions of time. So, we have two equations and two unknowns, and the unknowns are L and H. The trivial solution of this guy being equal to 0 and this equation being equal to 0, the trivial solution is L of t is equal to 0 and H of t equal to 0. So, this is one of the is an equilibrium point, and remember in the previous example which we gave, we had a single I mean a one dimensional system. So, the equilibrium point was just one single scalar value. Now, the equilibrium point x naught is basically 0 comma 0, all right. That is one equilibrium point, and this is the trivial equilibrium point. It is not very interesting, because it basically says that you start off with 0 tigers, 0 deers in the jungle, and of course, what will happen to your dynamics, they will always remain at 0. This is not this is not interesting. Okay. That is what. Now, what about the other equilibrium point? If we solve these two expressions, these two algebraic expressions, you are going to get this as your equilibrium point. Okay. RL by A2 and RH by A1, and so I will just call this as step 1. So, first we had the nonlinear dynamics, step 0. Now, we computed the equilibrium points, we are going to use this one and not the other one. And now, let us see for step 3, which is to compute the Jacobian. And how do we compute the Jacobian? We use the expression which we had before, which was partial f by partial L, partial f by partial H. So, I will call this f1, partial f2 by partial L, and partial f2 by partial, actually it should be H in our case, and partial L. Okay. Where f1 is nothing but RH times H minus A1 LH, and f2 is nothing but minus RL times L plus A2 LH. So, with these two functions, if I actually compute the Jacobian, this is the expression which I am going to get, right. So, this is the step 3, step 2. Now, in order to derive the linearized system, we know that we are going to essentially substitute the values of H and L into the Jacobian over here. Okay. So, when you do that, so this is going to become basically this expression over here. So, into the Jacobian, if we substitute RL by A2 and RH by A1, which is the equilibrium point which we had over here, into this, if right. So, if we substitute this into the Jacobian, you are essentially going to get this linearized matrix. So, this is actually the A, and with this we actually get your x dot equal to A times x. Okay. And of course, every time we see the linear matrix A, and you can see that it is linear, we do not have any coupling parameter. In the previous example of the nonlinear system, we saw that we had the coupling parameter A L H. So, this was the nonlinear term. Now, those terms have disappeared over here when you evaluate the Jacobian at the equilibrium point. So, now we have x dot equal to A x. So, this entire Jacobian at the equilibrium point is A, and we would always, first thing you would always do is to compute the eigenvalues. And when you compute the eigenvalues of this matrix A, in this particular case you see that the eigenvalues lie on the imaginary axis. Okay. And when you actually do the simulation of this, which I will show you in a few minutes, you will see that these eigenvalues, they produce a very interesting behavior, that the equilibrium point which we have considered, that is this one over here, the equilibrium point actually behaves in a very unique way, which is called as a stable center. Okay. So, how would that look? We saw in one of the previous examples in the previous lecture that an equilibrium point, one of the definitions is that if you start off at an equilibrium point, your dynamics always remains in that equilibrium point for all time in the future. Okay. Stable center has a very unique understanding or notion of what the dynamics would mean, and it basically would say that if this is an equilibrium point. So, when I evaluate these two values, right, and I get this particular point over here. So, this would be my RL by A2 and RH by A1, and if you start at the equilibrium point, as by the definition, and we will also see in the simulation shortly, the dynamics will tend to stay at this point only, it does not go anywhere else. Now, because it is what is called as a stable center, it has the following really interesting behavior. If you start at any other initial condition, okay, any other initial condition, the final behavior of the dynamics when you plot H of t versus L of t, okay, this behavior will always be a closed orbit or a closed response, if you want to call it, around the equilibrium point. Start at any other initial condition and it will go around that equilibrium point. Start over here, it will go around that equilibrium point. If you start somewhere over here, it would actually tend into this part of the axis and then again create a new orbit, and so on. So, the concept of a stable center is that you have an equilibrium point as before. If you start your dynamics initial condition at the equilibrium point, the dynamics will always stay there. You start anywhere else around the, in a neighborhood of the equilibrium point or anywhere else in your phase space, that is the space of your state variables, anywhere else it will be a closed orbit above that equilibrium point. And we will see very quickly that these closed orbits basically mean that the dynamics are basically oscillating with respect to each other. So, this orbit basically means that when the population of the deers is increasing, say assume I am at this particular point, and the population of the tigers is actually reducing. At the same time, you see the population of the deers is increasing. and it keeps increasing until the population of tigers have completely come down. At this particular point, the population of tigers starts going up and the deer population starts decreasing. So, if you actually plot this response, you will actually see that if the tiger population was going like this, the deer population would follow this, but with a slightly with a slight delay. So, every time the tiger population goes up, the deer population would come down, and when the tiger population is coming down, the deer population would actually go up. Okay. So, you will see this kind of a response. That is basically an outcome of how these closed orbits are there. Okay. So, now we talked of the center. It turns out the other equilibrium point which we did not consider, which was a trivial one, where did that go? Yes. So, where L is equal to 0 and H is equal to 0, it has a specific mathematical property that is called the saddle. We will not really go into those things. We are more interested in this equilibrium point, which actually has some physical meaning. Okay. So, now that we have our linear system of this form, let us actually and we know that the eigenvalues are like this, and we expect to see a stable center. Let us actually go ahead and simulate this in MATLAB, and we will see what kind of responses we are going to get. Okay. So, this is a code which basically simulates your predator prey model. It is called the Lotka-Volterra because that is the formal name of this one. Okay. So, basically the code runs like this. We are going to simulate it for 50 seconds. That is actually a little bit too long. We will just do for 30 seconds. And the parameters which I have taken, so the growth rate of the deers is 3, the natural death rate of the tigers is 1. So, that was a minus RL times L of t, and then the interaction parameters for the deers is 3 and for the tigers is 1. Okay. Now, these have been chosen not with any specific ecological model in mind, it is more a mathematical simulation. But if you have actual data from say any forest system, you can actually substitute these appropriate values. And the equilibrium point is defined over here. It was RL divided by A2 and RH divided by A1. Okay. So, that is over here. Now, let us say the initial condition. Okay. So, this is the number of deers. This is the number of deers, and this is the number of tigers. And the initial condition, we usually assume that the number of deers is much larger than the number of tigers, right. Otherwise, all the deers will die, eventually tigers will starve, they will also die, but that really does not happen in most ecological conditions. So, number of deers is more than number of tigers as an initial condition, and then we use this function from MATLAB called the ODE 45. Okay. So, ODE 45 calls a function called DEQ1, which I have defined in the previous line number 16 over here, and it says that we need to simulate it for about 30 seconds with these initial conditions. For those of you for whom it is not clear what is this ODE 45, what is this DEQ1, the best thing to do is to just type help ODE 45 in MATLAB, and it gives an excellent introduction to what you need to do, and it in fact gives a very specific example as well. Okay. So, either in this, or you can go to Google and check any of the examples for ODE 45. Okay. Let us see how the simulations look like. So, what I am doing here is to first in line number 20, I am plotting the equilibrium point with as a star, and then when I start my simulation. Okay. So, you can see that in this particular line over here, I have computed the solution of my dynamical system, right. So, the solution basically is H of t and L of t. And for H in MATLAB, I have called it as x of 1, for L I have called it as x of 2. So, x of 2 are the number of tigers and x of 1 are the number of deers. So, the solution basically will have two columns. The first column will be the number of tigers, number of deers as a function of time. second column will be the number of tigers as a function of time, that will be the solution. T is of course the time vector which is returned by this ODE45, it is an internal MATLAB function. Okay, so now this small piece of code, it takes each value of my solution, each population of tiger, each population of deer, plots it on the graph. Then it holds the graph, moves to the next value of the tiger population, deer population, again plots it, and so on. It is basically an iterative process. Okay. This final thing over here, it plots the time series of x and y, like what I told you before in the slide. So this will basically plot the population of tigers as a function of time on the x axis, and population of deers as a function of time. Okay. So we will see how all of this looks like. Now the interesting thing about this particular piece of code is that it allows me to actually see how this plot actually rotates or evolves. So let us go and click on run, and please remember this code will be available for all of you. Okay, you can see that this is how the dynamics is actually evolving. Okay, from the particular initial condition which we have chosen of 10 and 3, which is somewhere over here. Right, we started at this point and then it evolves like this. So this is the closed orbit which I was talking about. Initial condition was somewhere at this point, okay, and then it just goes around in this. Now we can see in black I have plotted the number of deers, in blue I have plotted the number of tigers, and always notice there is a slight phase difference between the two, and that is basically, we can explain that as follows. So let us start at this particular point on the time axis, say around 6, it could be months or years, around 6, and we can see that the number of deers keeps increasing very fast because there are very few tigers left in the jungle, right. So the number of deers keeps on increasing, and at some particular point the tigers have now access to a lot of deers, and it is very easy for them to hunt. So then the tiger population also starts to increase, right, and when the tiger population starts to increase and reaches a certain critical number, now the tigers are able to hunt the deers very well, and the deer population starts to fall over here, right. So this cyclical process keeps on repeating. For those of you who may actually be a bit skeptical about why these mathematical models will actually represent the true condition, it has been proven in ecology that if you sample data for, they have done an experiment with hares and foxes, and they have sampled the data for almost 100 years or even 150 years. The behavior over a large time scale actually looks like this oscillatory behavior with a slight phase shift, alright. Of course, when you actually look at shorter time intervals, the behavior will be fairly different, but in the larger time scale they will actually look very similar to this. Okay. Now we started at one particular initial condition 10 and 3, let us see what happens at different initial conditions. So let me just say I have got 6, 7 deers and 5 tigers, and you simulate this, you are going to get exactly the same kind of behavior, right. So this goes around and around the equilibrium point, this is a stable center, okay. And once the plot is complete, we will get this graph as well. Now you can see the numbers have changed because the initial condition of the tigers and the deers were different. So this behavior, which is a numerical simulation of a nonlinear equation, actually agrees with what we expected to get from our linearized model, okay, where we predicted that we are going to get a stable center, and the simulation of the nonlinear dynamics has shown exactly the same behavior. Okay, so in the previous example we have seen coupled nonlinear differential equation, the predator-prey model, and we saw an example of what is called a stable center, which is a particular type of equilibrium point. We also showed that with respect to the equilibrium point, the predictions which we make true are also, we have shown that in the simulations we get the same prediction of the stable center, alright. So in that particular case we were, it was nice that the predictions did with the linearized model did agree with the nonlinear case around the equilibrium point. Okay. So, let us move on to another example of the van der Pol oscillator, and this is basically an example of an oscillator with nonlinear damping, which you can see in this particular term over here, right. So, if you think of this as a mass spring damper or a RLC circuit, so you would see that roughly speaking this would look something like this: m d square x by dt square, we are talking of the differential equation, let us say plus b dx by dt plus kx equal to 0, right. So, this would be the example of a mass spring damper. In this particular case we have just assumed m equal to 1, k equal to 1, and this damping term is of a specific kind, it is of this type, alright. It is a nonlinear damping term, and there have been various applications of the van der Pol oscillator. So, people in biology, when they are studying the behavior of neurons in brain under certain task related conditions, they have actually shown that you can actually do the modeling with the van der Pol oscillator. It reasonably agrees with the experimental data as well. Okay. And the classical engineering example for the van der Pol oscillator is a tunnel diode. It is basically a diode which allows us to do very high speed switching in electrical circuits. Okay. So, now let us take this particular nonlinear differential equation. We see that this is where we get the nonlinear term. We will again repeat the same process and see what kind of behavior we can extract out of this one. Okay. So, before we do that, let us simplify the problem one step before, and what we will do is to assume that this parameter mu is equal to 0, right. So, when we assume that mu equal to 0, this entire nonlinear damping term actually goes away, and you basically get this expression dx t square x by dt square plus x is equal to 0. And we will now show very quickly that this is basically the dynamics of a harmonic oscillator. So, let us model this as a state space system. So, what we are going to do is to introduce two variables as what we did before as well. It is a second order system. So, we will introduce two variables. We will call the first one as x1, and I will just denote that to be x itself. We will call the second as x2, and we will call it as dx by dt, alright. So, from this again as we did before, we see that x1 dot is nothing but x2, and x2 dot is nothing but x1. Sorry, x2 dot is nothing but d square x by dt square, and d square x by dt square now we can write by looking at this expression over here as basically nothing but minus x. And what is x? We use this expression over here, and x is nothing but x1. So, if I put this now in a state space form, we actually get dx1 by dt, dx2 by dt is of course the states on the right hand side, and the interconnection matrix will be nothing but 0, 1, minus 1 and 0. So, if you actually do the modeling of an mass spring system, or if you do the modeling of a LC circuit, okay, so no resistance in the LC circuit, no damping in the mass spring system, you will actually get exactly the state space equations. And it is very easy to show that the behavior of the state space system is an oscillatory behavior. So, if you plot any one of the states as a function of time, you will actually get a perfectly oscillatory behavior, alright. In fact, a small exercise for all of you, please compute the eigenvalues of this system, and you will see that the eigenvalues will lie on the imaginary axis, okay. And when the eigenvalues lie on an imaginary axis, we have seen before it produces the behavior of a center, right, a closed orbit. So, in fact, if you plot the phase space, and remember the phase space basically is a plot of the states, it is very nice to plot this because it actually gives very interesting insight into the problem. You plot the phase space of this and it is going to look exactly like this, assuming we start at some initial condition over here, start at a different initial condition and you are going to get this kind of a response, so on and so forth. Okay. Right. So, what I just did in this slide was to consider the van der Pol oscillator. We remove the nonlinear damping term over here by assuming that mu equal to 0, and we get this expression over here. This expression is basically the dynamics either for a simple mass spring system or a LC circuit. In the state space form, it looks like this. Not really very relevant in this particular discussion, but the structure of this matrix, this is actually called a skew symmetric matrix. The structure of this matrix is very interesting and it leads to really beautiful insight into the analysis of such systems. We will not be needing it here, but if any one of you is interested, just look at skew symmetric and property of energy conservation. All right. And you see that indeed this structure, the 0 1 minus 1 0 actually leads to really interesting properties. Okay, so we are done with the harmonic oscillator, which is a special case of the van der Pol oscillator. Now, let us not assume mu equal to 0, let us assume that mu equal to 1, greater than 0, specifically mu is equal to 1. Now, when we assume mu equal to 1 and we compute from the differential equation, we compute the state space model, okay, same way as we did before. So, we will since it is a second order system, we will introduce two new variables x1 and x2 and we will relate these to each other through the interconnection matrix. And when you do that, you are going to get this state space model. All right. So, dx1 by dt is x2, dx2 by dt is this one. Okay, let us see what we can do with this guy. So, we have the model here which I am recalling in these two expressions, and for this we can compute the Jacobian. Now, because it is a second order state space system, we will have a 2 cross 2 Jacobian. Just to help you calculate this, it will be a 2 cross 2 Jacobian and you will essentially just compute the partial derivatives as follows. Right. For f1 we take the partial derivative with respect to x1 and x2, for f2 we take the partial derivatives with respect again to x1 and x2, and when you do that you are actually going to get this expression. So, if I so this is my f1 of x1 and x2, in this case x1 term does not exist, this is f2 of x1 and x2. So, when you take the partial derivative of this expression with respect to x1, since x1 term does not exist, this is nothing but 0. When you take it with respect to x2, you simply get 1. Okay. Similarly, when you take the partial derivative of f2, this expression with respect to x1, you would get minus 1 minus 2 x1 times x2. Okay, because this gets you take the derivative of this, which is basically 2 x1, then you have the negative sign. And finally, when you take it with respect to x2, you just have this term over here, this comes out and you get 1 minus x1 square. So, this is my Jacobian, which we also have over here. Okay. Now, of course, we have the Jacobian and in order to go ahead and linearize the system, we would also need the equilibrium points. In order to get the equilibrium points, we do the same trick as we did before, or it is not really a trick, it is a procedure. We just set dx1 by dt is equal to 0 and we set dx2 by dt equal to 0. Okay, set each one of these equal to 0, and then when you compute the Jacobian, the equilibrium point, you will see that this is the solution of the above two equations. Okay, there is no other solution in this particular case. X1 has to be equal to 0, x2 has to be equal to 0. Then you take this equilibrium condition, substitute it back in the Jacobian, and you are going to get your wonderful linear system over here. In this particular case, I have replaced the variables x1 with x dot and x2 with y. Okay. So, now let us analyze the property of this system. And the way we are going to do that is again and the way we are going to do that is to again, as we always do, we compute the eigenvalues. Remember in transfer function how we used to compute the poles, that is really the first step you would always do. So, similarly compute the eigenvalues of the system, and you will see that the eigenvalues are on here. Okay. So, if you look at the S plane or the pole 0 map, you will find that the eigenvalues are over here. Okay. And what do we learn? What have we learned from basic controls? That if the poles are in the right half plane, you actually have an unstable system. So, what we have basically done is to consider a nonlinear system, linearize it around an equilibrium point, get this linear system, and we have shown that the linear system here is unstable. Now, it is not unstable in any random way, it is unstable specifically around the equilibrium point that we have considered. And this is an interesting distinction, because what I mean by unstable around the equilibrium point is not the same as unstable at the equilibrium point. Okay. So, you will see very quickly that let us say that the equilibrium point was 0, 0, right. So, x comma y equilibrium point. So, I will call it x naught y naught. If I start at 0, 0 as the initial condition, as per my definition I should be stuck there forever, and you will be stuck there forever. There is absolutely no way that you are going to escape from the equilibrium point. So, it is not unstable at the equilibrium point, it is merely unstable around the equilibrium point. So, if I start anywhere else around that equilibrium point, we are going to see what actually happens, and actually you will see some very interesting behavior, that although your linear system claims it is unstable, and you will see very weird responses when you look at the transfer function, which I will be doing in a couple of minutes. It is not unstable in the sense that this is going to blow up, right. It is not like your oscillator is going to heat and blow up or cause some catastrophe. It is actually going to do a very interesting, it has a very interesting behavior. Start anywhere around the equilibrium point, and you will see that it goes into what it goes where is this? Okay. It goes into what is called as a limit cycle. Start anywhere around the equilibrium point and it will always reach the limit cycle. And in fact, in this specific example we will see that you start anywhere else in your phase space, any initial condition, it will always converge to this limit cycle. Okay, and we will see this in the simulation. So, the limit cycle is a very interesting behavior. It is actually telling us that wherever you start in the system, anywhere you will always converge onto this limit cycle, except if you start at the equilibrium point, because if you start at the equilibrium point you will be stuck there forever. Okay. So, we will see indeed that this behavior which plotted over here, this is actually what is called as a limit cycle, and you start at any initial condition wherever you want, okay, except at the equilibrium you will always tend to the limit cycle. Okay. So, let us see how this actually looks like in MATLAB. Okay. What we saw with the van der Pol oscillator, so we saw that the eigenvalues are in the right half plane, and which means the equilibrium point is unstable. Now, I have got this small MATLAB code, again like the predator prey problem, we will be sharing the code with all of you. Let me show one specific thing, that let us actually start the simulation at the initial condition. So that I will show you that if you start at 0, 0 the initial condition, you will always stay there only, because this is the equilibrium point. Okay. Like we did with the predator prey model, we again uses ODE 45, the same type as we did before. What will change of course is the model of the system. Okay. Good. So, if I start the simulation by assuming the initial condition is exactly 0, 0 the equilibrium point, you will see that there is really no dynamics. right, everything is exactly at 0 comma 0, okay, perfectly there, it never moves anywhere else. Now, we have said that this is an unstable equilibrium point. So, let me just perturb a little bit the initial condition along x direction. I can do it along y, it has the same behavior. So, when I perturb it along the x direction by this factor of 10 power minus, I do not know, 6 or 7, whatever this is, and then I do the simulation, because it is an unstable equilibrium point, it is not supposed to stay there, right, and that is exactly what happens. So, so we have started off slightly away from the equilibrium point at this particular place where my mouse is pointing, and because it is an unstable equilibrium point, it actually spirals out of that. Now, the reason it is spiraling out of that is because it needs to spiral and go towards this larger object over here. Okay. This larger object is a closed orbit, this is the limit cycle, and it will always go to the limit cycle. Okay. So, this basically proves that your equilibrium point is not stable. What happens if we start at different initial conditions, right? So, for example, let me start at 3 point whatever that is, right. Maybe I can make this as 2 and we will see what happens. Will it go to the equilibrium point? It will not, we know it is unstable. Where will it go? Well, it again tends to the limit cycle, right. So, I started over here and then it tends to the limit cycle. In the previous case, we started almost close to the equilibrium point and even that went to the limit cycle. Let us try this for a lot of initial conditions and we will actually see a family of solutions for each of the initial condition. Okay. So, what I have done here is to take 20 possible choices of initial conditions, and from each of these values 0, 1, -1, 3, -4 and 4, I am actually choosing a value for the initial condition. So, in my case an initial condition could, for example, be 0, 4, it could be, for example, 0, 4, right. It could also be -1, -2, it could be -1, 4, it could be 0, 3, so on and so forth. For each of these initial conditions, when you actually compute the solution and plot it, you are actually going to get this. So, this beautiful looking graph basically tells me the following: wherever you start from, whether this is the initial condition, this is the initial condition, or this is the initial condition and so on, wherever you start from, the final simulation will always tend to the limit cycle every single time. Okay. This is true as long as mu is greater than 0. If mu is less than 0, then if mu is equal to 0, we see that it will just be a perfect circle, which is a perfect oscillation because it is a harmonic oscillator. Okay. So, we also see that as long as the values of x and y are larger than 0, either x or y are larger than 0, okay, it will always tend to the limit cycle. If both x and y are equal to 0, it will get stuck at the equilibrium point. Okay. So, there is actually one specific case where we got x was 0, y was 0 initial condition and it stuck at this equilibrium point, this brown color plot. Otherwise, you see this beautiful looking graph. Okay. Okay. So, we have seen the example simulation in MATLAB that we obtain what are called limit cycles, as we see in this plot as well. We have seen the notion of a stable limit cycle, we have also seen the notion of a unstable equilibrium point. Okay. So, that concludes lecture part 2 of lecture 2, which was focused on nonlinear systems and the linearization of nonlinear systems. Okay. So, the linearization of nonlinear systems. We have taken 2 specific examples, the predator-prey problem and this van der Pol oscillator. Both are nonlinear systems and we have shown how we can linearize them and what interesting behavior we actually get. Okay, so thank you very much, and if you want additional references, they are over here. All right, thank you and good luck.